So we're here tonight to welcome one of our science visitors, Lex van Geen. C'est comme ça? Super. So this year at the Institute, we began hosting short-term science visits by scientists from Colombia in an effort to broaden the dialogue between disciplines and cultures that take place at Reed Hall in general and at the Institute for Ideas and Imagination in particular. And we've been very fortunate that Lex has agreed to be with us for a few weeks. And after Jeff Schlegel-Milch and Mo Ramo, who visited earlier this year, Lex is our third guest from Colombia's new climate school. Needless to say, we're very keen and honored to develop strong ties with such an important school, the first of its kind to be set up in America. A geochemist, Lex is a research professor at the Lamont Doherty Earth Observatory and is a member of the Earth Institute's faculty at Columbia. For 2 decades, he's coordinated earth science and mitigation efforts under Columbia's Superfund research program on the origin and health effects of elevated levels of arsenic in groundwater. In his talk tonight, Citizen Science Detecting Pollution Around the World, Lex will provide insight into the heterogeneous distribution of toxicants in the environment and how putting field kits in the hands of non-specialists can reduce exposure significantly, particularly in developing countries. Lex works with public health and social scientists and helps communities produce maps, raise awareness, and get the attention of elected representatives. In its mission statement, the Climate School aspires to develop and inspire knowledge-based and educate future leaders for just and prosperous societies on a healthy planet. With simple solutions that go a very long way, Lex is a great ambassador for such a mission, and it's a great honor to have you tonight. Thank you.
Thank you, Marie. Wonderful to be here. It's been fun, and it's such a beautiful place as well, which is inspiring. So this is going to be probably a fairly short presentation, but that's because I actually want dialogue. That's what I'm hoping. So here very briefly, and where I work, so my building happens to be this one. It's the latest, the most recently building built on the Lamont campus, which is not the main Columbia University campus. For those who don't know, you have to cross the George Washington Bridge and drive for about 15, 20 minutes to the north. But this is a lab that was essentially an estate that was given to Columbia in the 1950s by the widow of Eisenhower, in fact. I'm sorry, it was given by the widow of Thomas Lamont, and there's a picture where she gives the deed to the property to Eisenhower, who was president of Columbia University at the time. This talk is, I'm going to essentially show mostly maps and try to get some of your reactions to these maps. I'm going to talk about contaminants of various types. I'm going to talk only now about air pollution, which in the last decade or two really has come to the fore in terms of being the cause of a lot of deaths throughout the world that people did not realize for a long time. But it's not my specialty. Here I'm showing you actually a map of Manhattan, Lower Manhattan, Brooklyn, and Queens again. My colleague Steve Childred and others gave little portable air monitors, pollution monitors, to cyclists around New York City. And so they wore that and were cycling around at various times of the day. And you can, and the reason I'm showing you here is to illustrate this point that Marie referred to, which is how heterogeneously distributed these contaminants are. So even though these people were not driving at the same time, you can see some patterns, like this part here clearly with very high levels of pollutions, and others much lower, systematically lower. And that, I think, is a valuable piece of information. If you only had 2 or 3 government monitors set up here, you would not get this sense. You would not see this. So that's how much I'll talk about air. I'll talk about soil, water. I'll skip fire because I don't have too much to say about that. The soil here, that happens to be lead around an open mining pit in Peru. I'll delve into that to some extent. And this is a map of Bangladesh showing a village with a whole bunch of wells, hand-pumped wells, and their arsenic content. So that is what I'll be talking about. The main points I'll try to get across, I try to summarize those here. this notion of spatial distribution. And also the fact that if a hazard, a risk, a toxicant is so heterogeneously distributed, you can't expect government to do all the testing for you. And so that introduces this notion that we have to be part of the exercise, otherwise we'll keep getting exposed. Hence the emphasis on field kits. Field kits have their limitations. They're not always, they're certainly often not as reliable as a lab, but sometimes you don't need 5% precision when something varies across from 1 to 10 to 100 to 1,000, right? 50% precision would be enough in such a situation already. But there are also some issues of privacy. So if you do make these measurements, you make them in your own garden. Should others know about them? You make them in the park. Will government always let you make measurements in the park? All these are sort of intertwined to some extent. So that's the main theme. So let me spend a bit of time around here, the city of Cerro de Pasco. So at about 4,000 meters altitude in the Andes, pre-Columbian silver mines, started there. And now there is this enormous pit here. You see, look at the scale. This is 2 kilometers. So essentially, it's a kilometer-long pit in the middle of a town, and that's because the town was built around the mine. The mine provided the jobs. Today, when you start a new mine, when a Canadian company goes to Peru and starts a new mine, it buys all the land around it. You would not have this situation. So this is a historical mine, and essentially the mine has been growing and pushing the inhabitant areas further out over time. So this is a trip that we took in 2009, and we had sort of not quite an inexpensive field kit, but we had a handheld X-ray fluorescence analyzer. It's a rather expensive instrument, and here's a student using it here. And you can even see in the back, you can see on the other side of the open pit what it looks like, the landscape. And so we walked around. Sometimes the mining employees weren't too happy about seeing us do that, but we were able to collect this data set. The colors here, not too surprising, reflect the severity of the contamination with respect to lead. Green essentially meets today's standard for lead content of soil in the US in areas bare soil where children play. There's much discussion that this will probably be lowered to something like 200 or 300 in the ppm in the near future. So keep that in mind. But what you can see is that we don't see all that many green points in this town. And there are plenty of children. And I can tell you that some of these red points are right in the middle of playgrounds, for instance. So there's a serious problem in this site. And some heterogeneity. Clearly, some parts of the town right around the mine that have the most red and black and blue points, and then some further off areas here don't have that. And I should point out that these gray areas here, those actually mine tailings. So these are essentially tall hills built with the tailings. This was the material that has been excavated. Any questions about this map? Yes?
So where's the lead coming from?
So it's not, it used to be a silver mine and now is a copper mine, but unfortunately the copper and the lead are associated. So you mine you'd like to get rid of the lead because you're interested in the copper, but you can't avoid it. A country like Chile is actually fortunate. Chile has copper mines, obviously, I think it's the biggest copper producer in the world, and it doesn't have this lead associated with it. So it's geological history. Good question. All right, and I'm starting with this project. The first one I'm going to talk about is Peru, is because it comes closest to sort of my dream in terms of citizen science. You can sort of see here why. And then I'll end actually on the Notre Dame story, where I'll show you to what extent the kits were too limited to really do a lot of work. And we'll have something on arsenic in Bangladesh in between. So this is a colleague of mine, Johnny Ponce, who was funded by USAID, so the main US development funding organization, and he has trained by now hundreds of high school students across the country to deploy a kit that was that was developed by a PhD student of mine, Francisca Landes. And what this kit allows you to do, and the procedure is to take a sample and analyze it with a compound that produces a color that reflects the amount of lead in the sample. And what Johnny managed to do is, in about a dozen schools, he managed to introduce 3 days, essentially, in the science curriculum of these students. And for them, this was a direct experience, to do something that's relevant in their environment. So we're now hoping to have discussion with the Ministry of Education, because there are thousands of either current mining or past mining towns throughout the country where something like that could be useful. So here they sieve the sample, there's a funnel, you put it in a little vial and things like that. So obviously this was during COVID time. And I should have shown you first, the area that we are closing up is on this area here, which was worrisome because it was so red, but it had very few samples. It turns out there's a high school in the middle of that area. And this is the map they produced. It's pretty amazing. Now, I should say this is their visual reading, their visual interpretation of the kit. So say on 1, 2, 3, obviously greenish is all right, and red is not. And you can see, well, maybe let me ask you, what do you see? So imagine yourself being in the class, you produce a map like that. What do you take from it? What should they, how could they interpret it?
The red is mostly along one of the main roads.
That's right. It's also towards the plant. This is actually the ore processing plant. So there is a pattern, yeah. Anything else surprising from this? I think the high school is located right in the middle, and there's a football field right there too that is highly contaminated.
So why is there a whole area that's not contaminated, it seems?
Well, that's mysterious too, of course. So these tailings, I mean, if you have a contaminant, spreading it all over takes work. It takes energy. It's not going to come by itself. And so I think what this reflects is, in some places there were reasons. Maybe this was a transportation path, trucks uncovered, the dust is very fine. But I didn't realize this 20 years ago, but most contaminants are not homogeneously distributed. It takes mixing to get them everywhere. On one hand, that complicates things. It makes it more difficult to say whether a particular location is contaminated or not. But there's also, and I'll get to that, there's also an advantage. That means you can avoid the contaminated area. We tested some playgrounds. We could make a distinction between the playgrounds that were contaminated and the ones that are not. So to me, this heterogeneous distribution is a friend as well.
Does vegetation have anything to do with it?
It's very dry. This is
all
very,
so
very
there's
dry.
no
Yeah. In this particular case, yes. Scott.
How about the prevailing winds? I mean, so this is all being, it's airborne and then it's satellite, and that's what they're observing. Also, I wanted to ask, how does this change over time? So we don't know the dates on these.
That's right. This is a snapshot. This is the snapshot. They collect surface soil. A lot of that may well be blowing around. Despite the wind and the dryness, we still see patterns. That's all I can see. So it probably goes fairly deep. So this is the kit results, and we have essentially a dozen sort of maps of various towns around Peru like that, and hopefully we'll expand it. How does that compare to the instrumental data? So now, so the students did something very useful. They went everywhere. They had a smartphone to collect GPS coordinates. They recorded a picture of where the picture was from. They did their analysis, but they also had the sieved soil, and that we can analyze either there or in the lab. And so we did that. I skipped ahead. This was just to show you their visual, the signals. So what they had to interpret is whether the solution, after putting the soil, 3 scoops of the soil in the liquid, shaking it for an hour, filtering it, adding a little pill of sodium rhodizonate, which happens to bind and form a visible precipitate with lead, they had to determine whether their sample was low, medium, or high. So you can see there's a bit of, you could imagine some samples being in the tradition and in the transition and not being sure, well, is this a high or is this a low? But there is a gradient. So that was how they produced their map. What I'm going to show you next, I hope, yes, is a comparison with the instrumental measurements on the same, solid phase sample. Now, there are reasons why they wouldn't be identical. This is what comes off in that solution. The solution in the little vial that I show you, it's supposed to mimic what happens if the child ingests the soil. So it is pH 1.5, slightly acidic, glycine solution. It mimics what happens if the soil is digested, and mimics how much of the lead could be absorbed by the intestine through the intestine of the child. But this is the instrumental measurements. And well, let me hear it. What do you think? How do these compare? Not too bad, right? I mean, so you mentioned the reds. If you do the 1-to-1, it's not perfect, and that is an issue. But overall, the kit did a pretty good job picking up the main patterns of the area. And so certainly, if you, as a policy, sort of a local government, you want to say, is this area contaminated or not? I think this, let's say, 50% of the samples are red. That's pretty robust. Whether a specific area is contaminated or not, that may be a bit harder to establish based on the kit only. All right. So I'm going to now discuss the performance issue a bit more because it's relevant to any of the kits that we work with. This is a somewhat different data set. I could produce a plot like that for what I showed you before. This is actually a data set that includes samples from Peru, from Paraguay, from India, from various countries. An organization, an NGO provided those to us. And they were subjected essentially in the lab to the same process. So we did two things. We took the soil, we extracted the amount of lead, and we measured the lead in the lab. So this is the reliable scale, if you want. So this is the amount of lead here. This green level that I mentioned for you here is around this dashed line here. And then, without knowing the results, two different students also rated the blueness of the vials, right? And so the ones that are red, they put them high, the yellow and the medium. Now, my question to you is, if the kit had been perfect, what would this plot have looked like? So all I've done is I've ranked them by how much there really is in the solution. And then I've colored the bars, and obviously this is a log scale, right? So we're going down 2 orders of magnitude. Here, a factor of 100. And I've ranked them according to the lab measurements, but I've indicated the visual color. So tell me, if this had been a perfect kit, what would you have expected?
The red on one side and the green on the other side.
Thank you, Wilfred. That's right. So how bad is this?
Okay.
It's not bad, right? But it's not perfect. So that's what I was trying to tell you. So this is, but I can tell you, I have discussions with public health scientists. We've been trying a couple of times to get a little company, a non-profit going to produce this kit. And they're telling us this is not good enough. You are telling people, you're giving them bad information. And then I respond and say, well, it's this or nothing, because the government doesn't have this $50,000 X-ray analyzer, in the town, even though they could if the mining company paid the proper, royalties and things like that. But they don't.
I was going to say, why should the burden be on the kids to get it right, as opposed to others, the state or whoever else, who shows that the kids are wrong?
Well, so that's an interesting question. The patchiness, I think, what I was trying to show you here, the patchiness, that probably even underestimates how patchy it is. And so to really cover this, you would need, 10,000 samples. That's not realistic anymore. So that's why. And so sure, it would be great if the government did, but it doesn't. So I'm sort of accepting that. Also, I mean, we have a proposal that we just submitted, in fact, with the French IRD, the Institut de Recherche et Développement. It turns out that there's a serious hazard of lead exposure in Ivory Coast because of paint. In fact, Florence, who is sitting here, is part of that project. And the hypothesis that we want to test there is could it be that if the mother of a small child makes the measurement herself, she will also be more likely to take action afterwards. So there's a double benefit potentially coming from that.
How long term is this? Do you know how much of this is temporary, or is it deep in the soil, or is it something where if a wind blows in another direction, the results can be completely different, and if you have a measurement which you're not able to reproduce consistently, will it weaken the case?
I expect the temporal variability is much smaller than the spatial variability, but it would take a big effort to demonstrate that. The fact that this pattern is there and has been preserved in spite of all this resuspension, but you have a good point. At the same time, I hear that argument sometimes by government officials say, well, we shouldn't tell people about this because we don't know how reliable the measurement is. And that always bothers me. But I don't always know exactly how to counter it. Yes?
If they have kits, and the kits are inexpensive, nothing prevents them from doing the measurements with some regularity. And in fact, that should be part of the training and the cost.
Are you now talking about the households or the government?
The household.
Yes, 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 yes. Well, Florence, how many times are we going to get people, families to test the paint, for instance? Yes, no, I think you're right. And going back also to the sort of the educational component, learning about measurements, reproducibility, mapping, all these things are things that you absorb while you go through this exercise. All right.
But you mentioned the government, you mentioned the families, but obviously there's the companies, the industrial companies themselves, no? That would be maybe even more of a socially...
You're right.
way of doing this.
You're right. This is a state-owned company. And at least in Peru, I'm told that means that they are allowed to do more things than maybe other companies would be. Also, if the mining started 1,000 years ago, there's always a way of saying, oh no, it's not us, it happened before. So the issue of liability is there. But if the company were forward thinking, you might say, hey, I'm going to give money to these high schools to do their own testing. Yeah, and it wouldn't cost them much at all. I think that's what you're alluding to, perhaps. And I think that would be a wonderful thing. We haven't succeeded that yet. Yeah. All right, so that sort of closes the, how are we doing in terms of timing? 7:30. Okay, and we started a little bit late. But so that closes essentially the first of the 3 examples that I'm going to share with you. So now I'm going to switch to something that I've actually worked on for longer. This I started, as I said, about 10, 15 years ago. And it's going to be about the quality of well water in South Asia. So unless there are questions, I'll switch to that. I'll switch to that topic. I hope you can see that these sort of points were covered in the case of lead in Peru. So this is a map of the area of interest. And shown in red here are essentially the large river deltas where arsenic in well water is a potential concern. So you have the Indus River Basin to the west, you have the Ganges and the Brahmaputra, you have the Irrawaddy River here, and the Red River here. So this happens to be a slide where showing with the yellow boxes areas where we've had testing programs ongoing. I'm going to be talking mostly about what happens within this box in Bangladesh. The colors, by the way, I should say, don't reflect the severity of the arsenic problem in this case. It's population density. I mean, it is a multiplier to keep in mind, but obviously, so it's Bihar and Bangladesh clearly are the most populous areas. So rather than the high school kids we worked with in Peru, this started a longer time ago. This was the team that did, I think, a remarkable job. So maybe first a few words about wells. So these are hand pump tube wells. Some of you maybe still see them. One thing that is a characteristic of South Asia is that water levels are very shallow. They're always less, than 10 meters below ground, and that means you don't need to push the water up. You can suck it up. You can create, almost a vacuum, and you can draw water from up to 10 meters. For practical reasons, actually more like 6 or 7 meters. And so surface water, high population density, poor sanitation. If you drink surface water and you don't boil it, you get ill pretty quickly from microbial contaminants. And so using wells is a way of essentially having a natural filtration system. Sure, the surface water is contaminated. The surface water makes it into these aquifers that you pump from, but because of all the sand in between, you're essentially filtering. You have a fantastic filter system. So that's why these wells are so popular. We estimated, based on our early work, that about 10 million of these exist now in Bangladesh. Essentially, every family has its own well. It costs about $100 to install a well up to a typical depth. It's not nothing, but clearly people value it. The lifetime of a well like that is about 10 years, and so since maybe the past 3 decades, on the order of 30 million of these wells have been installed. Think about how much money they spent on that, right? So 30 million, that's 300, so that's $3 billion was spent by Bangladeshi households to get better water. The problem is that what people didn't realize that is in that part of the world, many of these wells are high in arsenic. And the arsenic is of natural origin. It's essentially sediment, being eroded from the Himalayas and then put under certain conditions, which we don't get into, I won't get into details now, and that releases arsenic to the water. It's not only a problem in Bangladesh or in parts of Pakistan. The lower Mississippi River will have these issues as well, for instance. And New Jersey, in fact, so even closer to parts of New Jersey. So this team here, we provided them with some training. We gave them the kits. They had GPS receivers. And for a year and a half, they would go out into the field every day, and they tested on average about 12 wells in a day. They recorded all that information. And they did, this is what the kit looks like. So this is a completely commercial kit. We didn't have to develop it. People continue to try to improve it, but we found this one was perfectly fine. You put about 50 ml of water here, you put a scoop of tartaric acid here, and then some zinc powder. It's actually a 19th century German chemist, Gutzeit, who invented the method. And it's been used all along. What is quite nice about it, essentially it converts the arsenic to arsine, ASH3, for those of you who are interested, which is a volatile form of arsenic. It's also the most toxic. That form of arsenic then gets trapped on the little strip of mercuric bromide and then turns a color, shades of brown. And the amount of arsenic is proportional to that, is related to that color. So what these women did is they did this, 12 wells a day, compared it, and then they recorded that result. This is a kit. Well, because of the toxicity of the arsine, I said you don't want to dispose of it. So this one, I have a little bit more trouble imagining, just anyone doing that at home. But I could imagine, again, high school students doing that with some supervision. So this is the map they produced. So there are 50,000 data points in here in that year and a half. Just to give you an idea, so we had a supplemental grant for that. This cost us less than $100,000 for 50,000 data points. So it was really amazing what they did.
Each point is a well?
Is a well. And this is an area which is inhabited by about 300,000 people. 6 people per well on average. I mentioned the 50,000 wells. And there, just to maybe prevent a question, there is not much temporal variability. We've done enough monitoring there in this case. So we think this is a pretty good representation. So some comments. What does this map look like? Here's a scale here. There's the Meghna River. And this is this study area. Anyone want to volunteer something?
Not good.
That's right. So at least 50% of the wells, maybe it's the tricks of the plot and all that in Google Earth, but 50% of the wells have too much arsenic. Yes. Is it all bad news?
Well, could I ask a side question? What are the effects of that quantity of arsenic in the water on people?
All right. So this is one of the problems. A bit like that. They are visible for only a small proportion of the people who are actually affected. So some people get lesions and some cancers that have been linked to that. But it turns out that the main killer, this was essentially our main result on the health side, is that if you compare people who drink less than 10 microgram per liter, which is the World Health Organization guideline for arsenic, and you compare it to those who drink more than 100, so in that red category, in a 7-year period that we monitored, the exposed people were twice as likely to die. So it was a big effect on mortality, and the surprise was they didn't die from the cancers or the skin lesions, they died from cardiovascular disease. So that was we didn't know that. So we started essentially a cohort study. I wasn't planning to talk about, but we essentially recruited 12,000 people, and we followed them for 2 decades. And and the first sad exercise is, okay, who's still alive after 10, 20 years?
So it's long-term disease. It's not.
That's right. It's not you're poisoning someone. Yes. That's right. It's very different. That's right. It's chronic exposure. Yes, Bjarne.
In Grey, that's a river?
That's the river. Yeah, that's the Meghna River. Yeah.
You can say that to some extent, the further you are from the river, the less bad it is. It's not perfect, but
No,
yeah, it's a sign of a kind of a trend.
No, and actually, if you zoom in, in Google Earth, it's kind of fun. You can see that riverbanks often are the most affected. It turns out, though, that this area to the north, the blue, that's an area that is not subsiding as much as other parts. So it doesn't have as much fresh sediment that has been accommodated, has been put on top. So it's older sediment that has been leached over time. Essentially, the groundwater has flushed it. And so these people to the north are obviously much luckier than the ones to the south. All right, so now I'm going to zoom in just to a fairly random village and hope to get some more comments from you, unless you have questions about this one. So here's a typical village here. You see there's a main road going here. This is probably a textile plant here. And you see the wells here, the colored symbols here. So it's fairly representative, I think, of the average. Now tell me, what does this...
Pretty random, no?
Right. Is that good or bad?
You're lucky or not lucky.
Right. Look at the scale here, right? This is 160 meters. So suppose I live here. What could I do?
Trade with your neighbor.
Exactly.
Yes.
So it becomes a social problem, right? These are privately installed wells, right? I mentioned the $100. How can you convince people to share the subset of safe wells? For the area overall, I made a very simple sort of GIS calculation. Whereas 50% of the wells have a red or red in this sort of description, 90% of the people live within 100 meters of a blue or a green well. So there's tremendous potential. And so with some of my colleagues, we try to understand how we can do this. I can tell you that with some economists from Colombia, Margosha Marajevich and Alex Pfaff, we did the testing, and then we said, 2 years later, we said, okay, what are you drinking from? And just asked them. And it turns out that half the people with the red wells, within 2 years, were no longer drinking from red wells. So that gave you the... We told them result right away. That's right.
And so what did they do?
They switched. Some of them installed new wells, but a lot of them shared it with their neighbors. This was actually within 6 months. We did a smaller study as well.
Do you think the blue, if I was one of the blue dots up there, among all the red ones, how reliable do you think it's going to be?
Yeah.
To stay blue as it is?
That's right. So you really think about the instability of the system. You say, you start pumping from that well, will you draw in the unsafe water? It turns out that the main water consumption here is irrigation pumping. Essentially because of the rice fields that you can see here. So the amount that is being pumped by hand, because it is by hand, is it's less than 1% of how much is pumped for irrigation pumping. In spite of this irrigation pumping, which is not throughout the year, we've measured arsenic in enough wells that we know that it doesn't change. And it has to do essentially that the arsenic content of the well is regulated by exchange with the sand very locally. So the system, even if you have some migration of the high arsenic water in a low arsenic area, it will be absorbed by the sediment. But it's a good question. So the system is fairly well buffered. What we are more worried is about, if you are the one person with a good well, how many of your neighbors do you want to come in every day and come and pump on your well?
So how do they resolve that?
Well, so I can tell you, so the government is now, the government tested 5 million wells 2 decades ago, and now it's starting another campaign. We've been arguing for a long time, you should have a testing service available all the time in the village, and maybe we can do that for the high schools again. Yes?
What are the possible reasons for such a difference in the arsenic content in places which are so close? And we have any idea? Or?
I mean, that's why we were funded for 20 years. So as I tried to tell Wilfred too, it depends, to a first approximation, it depends to the color of the sand. If the sand is orange, which means you have a lot of iron oxides, the arsenic will stick to that. And if it's gray, because of reduction of the iron, it actually gets released. And this is, if you look at these rivers, you can see these meandering rivers. It's been changing over time, and so it's just a very patchy environment in the subsurface. How much of it has been flushed? How much has been just sitting there for a long time? But it's yes.
How does it affect the rice fields?
Yes.
Yeah, good question. So we had another project. So people were worried about that very much and said, oh, the arsenic is going to be taken up by the rice, and the rice, we're giving rice cakes to children very often. And it turns out that even if you have rice fields that are not irrigated with high arsenic water, because essentially you're creating these reducing conditions, anoxic conditions in the rice field by flooding them, you're even in an uncontaminated field, you will have more arsenic in the rice than there really should be. And in fact, in the US at least, it's recommended not to give rice cakes to newborns anymore. I don't know if that's percolated here. Yes, very strongly. So I don't think what it is affecting is the rice yield. So it's actually toxic to the plant, and so we've studied that. So, Scott had a question. Yes.
Yeah.
No. Good. Good.
Really interesting. So one thought is, if you test my well, you tell me it's red, let's say. But is it public knowledge, the results for everyone's wells? So that's one question. Another one, I remember, I could be wrong, but I remember you telling me before that the arsenic is obviously very spotty spatially, but also in depth. That if you dig a deeper well, I believe you can escape this problem. Is that correct?
That's right.
So now that's of course a lot more expensive.
So let's do the depth part. So if I were to essentially flip this plot and put, instead of the longitude, I would put depth here. Most likely, I haven't done it for this, but most of the blue wells would be, instead of 100 feet, they would be 150. So it's 50% more expensive, roughly. So in fact, that is the kind of information that we're trying to convey to groups. In fact, we're trying to...
Maybe the thing, sorry to interrupt,
No.
maybe the thing to do there is to get, well, either have a government, but leaving that aside for the moment, just getting neighbors to pool their resources. They're already kind of sharing the pumps anyway, but pool their resources to dig a really deep pump, and then it'll be convenient for that little...
Right. And I've discussed that with economists like Mushfiq Mubarak at Yale, for instance. And the difficulty is there, where do you put the well? Everyone wants the well. So do you have an auction mechanism? Who gets the well in their land and could actually exclude someone eventually? It's not simple. But yeah,
Well, there are, just a quick thought on that. The countries have to deal with this kind of thing all the time. And typically what they do, the one that gets the well, as it were, on her property, his property, would pay proportionally more.
Yeah.
For that convenience.
Yeah.
And everyone feels, okay, that's relatively fair.
That's right. But people do like to have their own well. You know, there isn't that much privacy to begin with in these places. So yeah. Yeah. Let me switch. So the other one, you know, the post. So this is sort of I haven't really discussed about privacy so much, but this is what we do based on the results. We post the results, and if I were, and what still bothers me is that if I were to do this in New Jersey, and everyone, you know, people would be very upset with me. They'd say, who are you to essentially brand my family as having been exposed to high arsenic, you know, and we know it's bad for the children, we know it's bad for the mothers, and all that. And that still bothers me. Yes?
Also reducing the value of the land, so it's not only branding.
That's right. Although there's this depth, you know, the fact that it can go a bit deeper is still true. But so this is a situation where there's a trade-off. You know, there's a public health benefit from making this information, even though it's on private wells, you know, known to everybody. But there is a cost, you know, and it turns out in Bangladesh there has not been pushback on this. But that doesn't mean it doesn't bother me still. What I can tell you we're doing, sort of on the behavioral side, with Prabhat Manuel, who is a student you know, Scott, since he was in the PhD program, we are doing one intervention that was Prabhat's idea. In fact, it was paused because of COVID. We are getting households, neighboring households, it's a randomized controlled trial, to essentially families to exchange coupons. We give to each family 10 coupons, and we say, exchange these coupons, this is before testing, exchange coupons with those families with whom you'd be willing to share well. You know, you don't always get along with your neighbor. So essentially, we're trying to codify the social relationships. It's not enforceable. There's no policeman who's going to come and enforce it. But it codifies things. It makes it public to some extent. and then we do the testing. And so the randomized controlled trial is essentially 50 villages where we do the regular testing, and then we see, okay, how many of you are still drinking from red wells after 6 months? And then we do the testing after the coupon exchange, and then we say how many of you are still drinking. And we are hoping that it helps, but we don't know. Sort of essentially, the idea is that if you don't know whether you're lucky or unlucky, you might be more willing to cooperate in the future. But yeah, so this privacy issue does still bother me. Very quickly now here on the performance of the kit. This is a plot of, so as part of this 50,000, the women you saw early in the picture, they were collecting vials, and those were analyzed in my lab. And so of those, I mean, they collected, I think, 5,000. I analyzed sort of a random 500 here, and I classified, 118 of those were blue, based on the field kit, 173 green, and 211 were red. And what I show you underneath, I don't know if that's the best way to show it, is what the lab results said for that same batch, right? So what this shows me is that of the 118 wells that were labeled blue in the field, actually most of them, the vast majority, were correctly labeled, but 9 of them should have been labeled green. And typically they are, with concentration close to that threshold. The threshold, I should say, is somewhat arbitrary. This value between blue and green is 10 microgram per liter. From a health point of view, there's nothing magical happening between 9 and 11 microgram per liter. So to some extent, these errors are introduced because people like clear thresholds. But the reality from a health point of view is that that's not the case. And some labels should have been labeled red and they were labeled green. So it's not perfect. I won't say that. But there's one thing that the kit didn't do. Does anyone want to see that? Maybe I've told this story before, Scott. Tell me, how about compare the blue and the red, so the two extremes, going back to Wilfred's point here. Is there something that you notice? Among the bad labels, you see, one thing I'd like to point out is not a single of the wells that should have been red was labeled blue, and not a single one that was labeled blue should have been labeled red. So the trouble areas is green, but that's not so surprising. It's in the intermediate range. So I still think this is not such a bad kit. All right, last chapter now. This will be more familiar. This was actually, I have the link here. I don't know who took it. So this is looking west. This is the Seine, and this is the fire of Notre Dame on April 15th. And so there was this yellow smoke. How many of you actually saw the smoke? Yeah, you remember, yes? You did. So you did as well, yeah. Did you think of the lead in the roof right away, or not even you, even though it's your business? Yeah, that's interesting. So that color, it turns out, is quite characteristic, that yellow color. So this is a data point that I think has maybe not been used enough. So the French monitoring system has a number of air monitoring stations and collecting filters. And there's one to the north of Paris in the 18th arrondissement here. And you can see that throughout this period, so we're talking about April 15th here, it's, there's some noise, but it's pretty flat. But the one that is 50 kilometers to the west of Paris, so way, way, way over here, clearly saw an order of magnitude increase in lead concentration. And that's far, far away. I don't think people have discussed this enough, and it was a really valuable data point. So that's why we put it in our paper here. The other thing I wanted to point out is
that there are only 2 places where I measured.
That's, yes, they don't have too many, yeah. So, yeah. One thing that the first organization that made some noise within a few days of the fire was actually an organization called Robin des Bois, which is an NGO, quite vocal. And the government, the Agence Régionale de la Santé, only responded like 10 days later with some information, and it was more of a, don't worry, we're taking care of it. It was really amazing still, I find today. So obviously, my hat off to Robin des Bois. So we, so Alessandra and I, we were here in, so we're now talking about, so 2019, so December 2019, January 2020, looking for things to do. And I thought, well, I haven't heard much about where this lead has gone. If there is 400 tons of lead, that's what the roof is made of, where did it go? The smoke was there. We get this reassuring information. How true is this? And so we did something very simple. I drew 2 circles around Notre Dame, one with a 400-meter radius and the other one 1 kilometer. And I said, well, I want to be somewhat objective, so let me just sample all these places. I knew a little bit about soil samples because of Peru, and so I looked for soil, and it turns out that there aren't that many places where you find the soil. Soil is interesting in this case because I knew that the firefighters had been washing the streets like crazy. The nice thing about soil is that essentially it retains the deposition, and so that was the argument of saying, well, let's find out. And I had no idea where this was going to go. So we did that, and we measured with the kit. These were our first measurements. And it turned out that 3 of the measurements were very high, close to the cathedral. There were maybe a dozen more, but by and large it was essentially below the detection limit of the kit. Okay, but based on this information, we went beyond the initial 2 circles.
Initially, you said the wind.
So the rim was towards the west. Towards the west.
Is west.
That's right.
Okay,
that's
so
right.
That's consistent.
That's right. It is consistent. But let me tell you, I actually was misled. I think I was not objective in my reading, and this is the actual. So I had these colors, and I had judged those, and then I measured them in the lab, and it turns out that this is what the pattern looked like based on the readings. So I was more or less consciously sort of projecting what I was expecting. It can happen to anyone. That was my point. So this is what we got. Yes, exactly. But then we had those sieve samples, and then we analyzed them in the lab as well, and that became more interesting because then you can start detecting more things. So when you actually measure the total amount of lead here I'm doing a slightly different color scale, in part because the regulation is not quite the same in France. In this case, so the greens are up to 100. So let's try to be objective. Look at this pattern. This is the total lead in these soil samples. What do you see? Do you think there is or there isn't an impact? Based on this, would you think there's an impact of the fire or there isn't? What makes it hard to sort of unbias your view?
The closer to Notre Dame, the worse it is, no?
Yeah, I think so too. Yeah. I think that's one argument. That's right. But it was somewhat biased sampling. Essentially, I could collect 100 samples here, and they would be high, and so you need a model essentially to then smooth that. But I think you're right. But you have the occasional, like in the Luxembourg, there was a high sample. Yes.
But you also don't have before or after, do you?
No. So that's.
It's all after. No?
It's all after.
It's all after. But there may have been some other source of lead.
That's right. Completely right. But the thought was, if the fire had an impact, and there is a directional, there's a direction that the wind was blowing, and that's pretty well established, then I could expect something in that sort of windrose sort of pattern, and it was there. So I was lucky. I had a statistician also. I should say, so on sort of privacy, public. So I didn't advertise this, and some people looked at me in funny ways. This is, I think, where we saw each other just a few, not looked at the study here. So there is a website where all these samples are documented. So the lab measurements and a picture, and this is the little sample bag when it was collected, and it's there. So you could, if you wanted to know. What I'm trying to say is that, this is an exercise, but why not have much more of that? Why not much more information like that, make it publicly available? From the student's point of view, it's interesting to make a map, use these smartphones for something, not just for watching YouTube videos and things like that. So they could do that fairly easily.
Does the lead remains in the surface?
So
if it rains and with time it can go deeper?
So that's a good question. It turns out that lead is very sticky. It really absorbs very strongly. Arsenic is sort of in between. And because of that, it will stay at the surface for a long time. But it's a good question, yes. And I'm almost there. So then I did have a statistician, a student of Andrew Gelman, Yuning Yao, who actually did the proper thing. So essentially making sure that even though I've sampled this place 10 times, that doesn't weigh my whole data set. And so he calculated from that, and I'm going to end up with a bit of perspective. So we calculated that within that plume to the west of the cathedral, so northwest of the cathedral, there was about a ton, between 1 and 2 tons of lead. 1,000 kilos of lead had accumulated. Put that in perspective, the whole roof was 400 tons. So it's actually a fairly small percentage, but it modified the composition of the soil. And what was interesting is that a French organization, ANSES, I don't know exactly what ANSES stands for, Florence, but anyway, did essentially, they looked at more from the plume perspective. They knew the plume dynamics, how much lead there was in the plume, what they estimated that. And they said that beyond 1 kilometer, about 150 kilograms of lead was deposited. And, you know, and so that includes the spike that you saw at the Limay monitoring station.
So where are the 390 plus of the top?
I think they're still there.
Where the water?
Where?
Do you mean of the roof? I don't think they took off. I don't think it burned away. So that's, I can constrain that. I think it just didn't volatilize. And I haven't seen the film yet. I think you did. And I think there's melting lead from the gargoyles and things like that. I haven't seen it yet. So even though this is a pretty crude exercise, it put an order of magnitude, you know, on how much was coming from that. And I think that's quite consistent. You could very well imagine that if, say, you know, 1,000 or 1,500 of something comes in that first kilometer, having another 150 beyond that, it seems to make sense. You'd expect some sort of exponential, you know, decay of some sort. But this is an important, I'll end up with this point, you know, so until not so long ago, lead was added to petrol, to gasoline. And it turns out, and I looked this up in a couple of ways, that in 1990, compare that ton, essentially 800 tons of lead were emitted in the atmosphere in Paris every year. And so sure, there was reason to be concerned about the lead from Notre Dame. The government could have responded in a better way by being more upfront and admitting that they are, you know, they're still trying to figure things out. But, you know, what a blessing that lead is no longer added to cars, to gasoline.
How did your analysis compare with the one that Paris did? Because I remember at some point they were thinking of closing schools and parks and things like that. So they did do a very, I don't know if it was a good one or a bad one, you tell me.
So it's interesting. So the early French samples here had these very high levels, and they were also picked up by the New York Times, close to the cathedral. But for any of the other values that came later, they were months later, and they were from hard surfaces that hadn't been flushed. And so I think they were underrepresenting the amount that had been deposited because of that. If I had one thing that bothers me about the government response is that they, after at least 1 month, if not 2, they said, oh, and if you're concerned about your child, you can go to Hôpital so-and-so and get your child tested. They should have been much more proactive. They would have said, you know, every child should be tested because, you know, if 10% of the children are going to be tested, it's going to be probably for the parents that don't have lead sources at home and things like that. So that I thought was a real mistake from a public health point of view. It should have been a much more proactive, you know, recruiting of every child and testing. Yes, there were some classrooms that were tested, but that was months later. I suspect that for a very short time, the Préfecture de Police, places that were really downstream from the cathedral, there was a école maternelle, Rue Saint-André-des-Arts, for instance. I expect they had high levels of exposure for a short time. And then they cleaned it and it went away. But keep in mind the 800 tons from the cars before that as well. So, all right, that's the end of my story. So this is a case where, if anything, maybe the kit was a bit misleading, but the fact of sampling and doing something very basic was still useful. And so I'm hoping in the coming years to spend more time on that, get more, you know, high school projects involved in these types of activities. So I had a story on fluoride. I took it out. It looks like I made the right decision because there was plenty of material here already. Thank you very much.
Thank you.
Lex, this is great. Really enjoyed this. So one thing I like about this is we're talking about public health, and you're putting, in a sense, power into the hands of the public. And we have governments, and their job is, I think, to look public, but they don't always do it in the best way. There's research showing that for your first case, air pollution, the location of monitors is very important. And it's basically a political decision where to put the monitors. I mean, you can just tell, is it the top of a building, is it inside a park? So that's a political decision. And it's been shown that governments will put it places where they basically won't be forced to do something they don't want to do. So one thing I like about this is you're kind of giving power to the people, as it were, and I think that's terrific. On the other hand, there's another part of this, which you just mentioned toward the end, which is one of the incentives for the people to really do this consistently and persistently, because if I go out and do the measurements, other people are going to benefit from that information if I make it available. So why should other people do it? So I'm sort of curious about how that, the two sides. I mean, it can't do any harm. It can only do good. And maybe the best way to think about it for a developed country is that it's a way to do it, let's say, periodically. I totally agree with schools doing it. I think it's brilliant. But to do it and then to use this to hold the government to account. Maybe that's probably the best balance. I don't know if you have any thoughts about that.
No, I agree. I think maybe the only thing that I would say is maybe we should do the same thing in developing countries. That would be sort of the starting point. And if we deviate from that, okay, let's think about it too, rather than assuming they should be treated differently. But yes, I can tell you when, for instance, in the lead study, I had someone from the IRS, I met with a person, and this person was very reasonable. So realized, was careful. I don't know why within governments it's not possible to essentially say, yes, we're overwhelmed, we're going to try to do our best, and this is what we're doing, and why there's always this sort of reaction to say it's under control. I don't fully understand that. I think it's a mistake, and maybe more citizen science will prevent that.
It's a question of panic. It's preventing
That's right. Yeah, that's right.
I think that's one thing. I think the second thing is, and we've seen that with COVID, the cost of a test can sort of distract funding into other places. Yeah. And I think the third thing, which I think is more relevant to the water example, is to what extent do you need the invisible hand? Do you need a water company or a state putting piping and connecting the different blue dots and pulling it together? And I think this is a great way of protesting and sort of citizen ownership. But shouldn't you reduce it to what is affordable for citizen ownership? And should you nevertheless also focus as much on what is the collective right solution? Because you don't want to have a nation of citizens doing their own thing independently from one another and not sort of connecting the blue dots, which makes sense, is the only thing which really makes sense in the long term.
I think you're absolutely right. The question is, what is this long term, right? So in Bangladesh, realistically, it could be 50 years. In the US today, 40 million people drink water from their own well. Of course, population density is very different in the US than in Bangladesh, which is like 1,000 per square kilometer. So I agree with you. There should be, you could imagine sort of a village committee. In fact, I have another colleague, Margosha Malivecic, who's trying to say, okay, suppose, how could we have a committee, a village organization decide the optimal location for a community well, so a shared resource. But often they aren't maintained as they should be, and there are some struggles. Essentially, elite capture, it ends up in the backyard of a powerful person. But you're right. I have something quantitative to say about this. We calculated the cost of lowering exposure in that area of 50,000 wells, based on all the information we had, including, say, community wells that were installed by the government. So these were deeper wells, about $1,000 each instead of 100. And we estimated that to lower the exposure of a person by well switching, so no effort, essentially it was the cost of testing, that's about $1 per person whose exposure has been used. And the government activities, they installed 1,000 wells in this area. The impact was limited because of elite capture and things like that. It was $100. So there's a long distance between those two figures. So I agree with you. The infrastructure eventually, But right now, the bit of infrastructure that's being done is very expensive and doesn't have much impact, unfortunately.
Thank you.